In stats, we wrapped up our conditional probability notes by talking about independence. So first off, we started with the rule, what it means to be independent, and that is if A times B equals A and B, then A and B are independent events. So that check, first of all, that's the rule. That check has to come out as true in order to say yes. So the example you see right below this is most likely going to ask that question about two different events. So you check if you can multiply the two different events to get the intersect. It doesn't always come out as true or false. The textbook way, another way, if A equals A given B, then independent. That's another way to check for independence. All right? I typically do it the first way I wrote, though. So for example, on this problem you see here, lefties down under, we want to check to see if male Australian high school students are independent of left-handed people. So I want to see if male times left equals male and left. So this is not an opinion that they're asking for. Many people think it is. They think it's an opinion, and you get a big old paragraph talking about how handedness has no bearing on gender, but that's not what the question is asking. It wants a numerical response. So first probability of male is 46 out of 100. 100 is a nice total, isn't it? Probability of left is 10 out of 100. And then the other probability we're going to need to compare is the intersect. So they cross with a 7. Now, you already probably see the answer. Please don't write they are not independent right now. You got to show the numeric proof. So you got to show 0.46 times 0.1 is not equal to 0.07. I would still write one more line and write this. Whoops, sorry, just rewriting. I would write this to show that they are clearly not the same probabilities when I multiply versus the actual intersect. So then I need to actually answer. I haven't answered the question yet. I want to say male and left events are not independent. Now, it is possible for one of these to come out as a true statement. I've seen it many times. You just have to show the numerical proof, and if the left side equals the right side, then you say they are independent. All right, moving on. Speaking of independence, if you already know that the events are independent, you're allowed to multiply. So that proof that I wrote at the top of the last page goes in either direction. If they say that they're independent, or you can assume that they're independent, you're allowed to multiply for multiple events to get the intersect. So this is a sad story about the Challenger, all true. The O-rings were what caused the the shuttle to not launch successfully. And supposedly, to launch successfully, all 6 O-rings had to work. Let's use the word succeed. We use that a lot in this next section of probability. That looks like 60, doesn't it? Maybe I should use the word 6. There we go. So we want to know all 6 had to succeed. Let's write it a different way. If we assume these are independent, see, they tell us that, and we know the probability of one success is 0.977. This would be the probability of the first O-ring succeeding, second succeeding, and so on. Right? So those are 6 S's. That's the intersect of 6 O-rings succeeding. That would be 0.977 times 0.977 times, and so on. Let's just raise it to the 6th power, and we got it. When we do that, we get 8697. And sadly, that probability is pretty low, I think, in speaking of living versus dying, because that means there's a 13% chance of failure. So pretty sad. Of course, that's hindsight. I hope they didn't know these exact values beforehand, but there it is. So I'm going to make another note. We can multiply .977 times 0.977, and so on, because each O-ring is independent. All right. That was all we did today. See y'all later.